For this video lecture, I want to go over the monoatomic and polyatomic ions. So first, let's talk about monoatomic ions. A single atom of a metal with a positive charge is called monoatomic cation. On the other hand, a single atom of a non-metal with a negative charge is called monoatomic anion. The names of the monoatomic ions is under the IUPAC's nomenclature rules. So IUPAC stands for the International Union of Pure and Applied Chemistry. IUPAC has set rules for naming ions and compounds. These rules refer to as IUPAC nomenclature, which are still in use today. First, let's talk about monoatomic cations. A single atom of a metal with a positive charge is called monoatomic cation. Metals atoms, as you know, can lose valence electrons and become positively charged cations. So cations are named for the parent atom, followed by the word ion. For example, sodium. When sodium loses one electron, it becomes sodium plus or Na plus. It's named sodium ion. For magnesium, when magnesium loses two valence electrons, it becomes magnesium 2 plus. Therefore, it is named magnesium ion. This rule applies for metals that usually form one ion. This includes the main group metals except for tin, lead, along with silver, zinc, and cadmium ions. However, metals that can form more than one ion, they can form multiple ions. If a metal can form more than one cation, it is named for the parent, followed by the charge in Roman numerals in parentheses, followed by the word ion. For example, copper can form two types of ion, copper 1 plus and copper 2 plus. For copper 1 plus, you will use the Roman numeral 1 put in parentheses. So it's named the copper 1 ion. For copper 2 plus, you will use the Roman numeral 2 put in a parenthesis and name it as copper 2 ion. This is called the Stokes system of naming transition metal gas ion. There's another naming system called Latin or surface system. For metal ions with two common ionic charges, you can use the Latin or surface system. This system takes the Latin name of the elements and adds the surface OUS or IC. The cation with the lower charge will receive the OUS surface, with the one with higher charge receive the IC or IC surface. The copper plus 1 is the cuprous ion and copper 2 plus is the cuprous ion because you see copper 2 plus has higher charge than the copper 1 plus. Now the Latin system is less common than the Stokes system that I taught in the previous slide. You can predict the formulas of the monoatomic cation. Recall that group 1A metal, 1A or 1 metals are always form 1 plus ion. Group 2A or 2 metals always form 2 plus ions. So we can predict that group 3A or 13 metal will form 3 plus ions. Not all metal ion charges are predictable. For example, tin and lead in group 4A or 14, they both can form 2 plus and 4 plus ions. Most transition metals form 2 plus ions from the loss of their 2s valence electrons. This table you can find in your textbook is some of these elements are reputable with their common charge. For example, in group 1A, you can see that lithium can form lithium plus by losing one valence electron. Sodium can form a sodium plus by losing one valence electron, and potassium can lose one valence electron and become potassium plus or K plus. Likewise, for group 2A, with the exception of beryllium, magnesium, calcium, strontium, and barium, they can lose 2 valence electrons and become magnesium 2 plus, calcium 2 plus, strontium 2 plus, or barium 2 plus. For the group 3A, you can see that aluminum can lose 3 valence electrons and become aluminum 3 plus. We talk about the transition metal that can form more than one, that have multiple ions, like iron 3 plus, iron 2 plus, cobalt 3 plus, cobalt 2 plus, copper 2 plus, copper 1 plus, mercury, and some for tin and lead we talked earlier. However, manganese in this table show one ion is formed, but in fact, manganese can have more multiple ions. For example, in the oxygen and bond complex in photosynthesis, manganese appear at manganese 3 and manganese 4. It goes through a different stage from S0, S1, S2, S3. Scientists spend most of the time, or all of their time, to search for which oxidation state or the ionic charge of manganese in this state. And up until now, I don't think there's an agreement at oxidation state of manganese in each of the state among the scientists. You can find in detail information about manganese ionic charge through this publication here. Now we talk about monoatomic cation, but elements can come together and forming polyatomic cations by losing electrons. For example, ammonium plus ion. This is only polyatomic cation you will see in our class. Next, let's talk about monoatomic ions, which are anions instead. So a single atom of a non-metal with a negative charge, we call it monoatomic anion. This table in your textbook shows the common monoatomic anions. For example, bromine ions, chloride ions, fluoride, iodide, or nitride, oxide, phosphide, or sulfide ions. So non-metal, we know that can gain valence electrons and become negatively charged anion. Monoatomic anions are named by dropping the end of the element name and adding the suffix IDE. For example, bromine, you can see that the INE in the bromine name is dropped and then replaced by IDE. So from bromine to bromide ion when bromine lose one electron. For example, another example is chlorine. When chlorine lose one, when bromine gain one electron, it become a bromide ion, and chlorine, when it gain one electron, it become chloride ions. When you name these ions, you would drop the ends of the element name. Like for chlorine, you drop INE and replace by IDE. For the fluorine, you drop INE and replace by IDE, and it becomes fluoride ion. Likewise for iodide, or nitride, or oxide, or phosphide, or sulfide ion. Just like the cation, you can predict the formulas of monoatomic anions. And you know that non-metals gain electrons to form anions in a predictable fashion. For example, in group 7A or 17, atoms gain one electron to form one minus ion, such as fluoride ions, chloride ion, bromide ion, or iodide ion. For group 6A or 16, these atoms gain 2 electrons to form 2 minus ions, such as oxide ions, sulfide ions, or selenite ions. Group 5A and 15, they gain 3 electrons to form 3 minus ions, such as nitride ion or phosphide ion. So we talk about monoatomic ions. Let's talk about polyatomic ions, such as oxyanions. So oxyanions, they are polyatomic anions. They contain one or more elements combined with the oxygen. So the anions, they are called oxyanions. So most oxyanions have named the N in the surface ATE. For example, the nitric ion, NO3 minus, the sulfate ion, SO42 minus, the permanganate ion, MnO4 minus. Now, some anions end instead of end with ATE, it ends in the suffix ITE. For example, NO2 minus is the nitrite ion, SO32 minus is the sulfite ion. You notice that the deoxyanions have one less oxygen than the ATE ions. For example, sulfates, you can see it have 4 oxygen. When it becomes a sulfite ion, it had 1 oxygen less. Here's only 3 oxygen. That's why for the nitric ion, when it becomes a nitrite ion, the 3 oxygen and NO3 minus become 2 oxygen and NO2 minus. So the oxyanions that end in ITE each have 1 less oxygen than the oxyanions that end in ATE. More about polyatomic anions. Now, if you know the formula for the chloride ion is ClO3 minus, you can predict the formula of the chloride ion. When the surface had changed from ATE to ITE, you know that chloride ends with ITE must have 1 less oxygen than the chloride ion. Because the chloride ion is ClO3 minus, it has 1 oxygen less in the ITE ion. Therefore, the formula for chloride ion is ClO2 minus. Notice that the charge -1 does not change as the number of oxygen atoms has changed. There are 2 common polyatomic ions that ends in IDE, the hydroxide ion OH minus and the cyanide ion CN minus. In your textbooks, there are a table for common polyatomic ions. Like I said, for the polyatomic cation, the only ions that you learned in this class is ammonium ion NH4 plus. For other polyatomic anion, you can see how the list of all of the polyatomic ion with the associated IUPAC name that you must know for this class.